The question of whether we are alone in the universe is one of the oldest and most powerful ideas in human thought. It begins long before modern science, long before telescopes or space missions, when early civilizations looked up at the night sky and saw countless points of light scattered across darkness. Even without understanding what stars were, people sensed scale, distance, and mystery. The sky suggested something vast beyond human life, something that might be filled with other worlds, other beings, or entirely different forms of existence. This sense of possibility is the origin of the search for extraterrestrial life, a search that has evolved from imagination into one of the most serious scientific pursuits of modern time. For most of human history, the idea of alien life remained in the realm of philosophy, mythology, and speculation. Ancient Greek thinkers debated whether other worlds existed and whether they might contain life. Some argued that Earth was unique and central, while others suggested that countless worlds could exist beyond our view. These early discussions were not based on evidence, but they introduced a powerful concept. If Earth is not unique in structure, then perhaps it is not unique in life either. This idea slowly grew over centuries, waiting for science to provide tools that could test it. The development of astronomy began to change everything. When telescopes were first turned toward the sky, the universe suddenly became more detailed and more complex. Galileo's observations of moons orbiting Jupiter showed that Earth was not the center of all motion. This realization was deeply important because it suggested that Earth might not be special in other ways as well. If other planets and moons existed, then they too might have their own environments, their own histories, and potentially their own forms of life. The universe began to look less like a single stage built around humanity and more like a vast system filled with countless possibilities. As science advanced, the idea of extraterrestrial life became more grounded in physical reality. Instead of asking whether life exists elsewhere in a purely philosophical sense, scientists began asking what conditions are necessary for life to exist at all. This shift was crucial. It transformed the question from imagination into analysis. Life, as we understand it, requires certain basic ingredients. It needs energy, a stable environment, and chemical building blocks that can form complex molecules. Once these requirements were understood, the search for life beyond Earth became a search for environments where these conditions might exist. One of the most important discoveries in this search is that the same chemical elements found on Earth are found throughout the universe. Hydrogen, carbon, oxygen, nitrogen, sulfur, and phosphorus are not rare or unique. They are produced in stars and distributed across galaxies through processes like stellar winds and supernova explosions. This means that the basic ingredients for life are widespread. The universe is not chemically limited. It is rich with the raw materials needed for complex chemistry. Carbon is especially important in this context. Its ability to form stable and complex molecular structures makes it the backbone of known life. In space, carbon is found in many forms, including simple molecules like carbon monoxide and more complex organic compounds. These molecules have been detected in interstellar clouds, on comets, and in meteorites that fall to Earth. This suggests that the chemistry of life is not restricted to planets. It can begin in space itself, long before planets even form. Water is another essential ingredient. It acts as a solvent, allowing chemical reactions to occur efficiently. In the universe, water is surprisingly common. It exists as ice on comets, as vapor in interstellar clouds, and as liquid beneath the surfaces of some moons. The presence of water in so many different environments increases the number of places where life might potentially develop. It also suggests that the conditions for life are not as rare as once believed. As our understanding of chemistry and astronomy improved, scientists began to consider where in the universe these ingredients might come together in stable and long-lasting environments. This led to the concept of habitable zones. A habitable zone is the region around a star where temperatures allow liquid water to exist on the surface of a planet. If a planet is too close to its star, water evaporates. If it is too far, water freezes. In between lies a narrow range where conditions might be just right for life as we know it. The discovery of habitable zones changed the search for extraterrestrial life in a fundamental way. Instead of imagining life anywhere and everywhere, scientists began focusing on specific types of stars and planetary systems. They looked for planets that were similar in size and composition to Earth, orbiting within the habitable zone of their stars. This approach turned the search into a structured scientific effort rather than a broad philosophical question. For a long time, Earth was the only known example of a living planet. This made it difficult to estimate how common life might be in the universe. But the discovery of exoplanets changed this situation dramatically. An exoplanet is a planet that orbits a star outside our solar system. The first confirmed detection of an exoplanet marked a turning point in astronomy. It proved that planetary systems are not unique to our own Sun. Since then, thousands of exoplanets have been discovered. They vary widely in size, composition, and orbital characteristics. Some are gas giants larger than Jupiter, while others are rocky worlds similar in size to Earth. Many of these planets exist in conditions that could potentially support life. Some orbit within habitable zones, while others may have subsurface oceans or atmospheres that protect them from harsh radiation. The study of exoplanets has revealed just how diverse planetary systems can be. Some planets orbit very close to their stars, completing an orbit in just a few days. Others travel along highly elliptical paths, experiencing extreme changes in temperature. Some are tidally locked, always showing the same face to their star, while others rotate in ways that produce complex day-night cycles. This diversity suggests that the universe contains many different environments where life might develop in ways we do not yet fully understand. As scientists study these distant worlds, they use indirect methods to learn about their composition. By observing how planets pass in front of their stars, they can analyze starlight passing through planetary atmospheres. This allows them to detect gases such as water vapor, carbon dioxide, and methane. These molecules are important because they can be associated with biological or geological activity. The idea of biosignatures has become central to the search for life. A biosignature is any substance or pattern that might indicate the presence of life. On Earth, life produces a wide range of chemical signals. If similar patterns are found on other planets, they could suggest biological processes are occurring there. However, interpreting these signals is complex because non-biological processes can sometimes produce similar results. Despite these challenges, the discovery of exoplanets has made the search for extraterrestrial life far more concrete than ever before. Instead of wondering whether other worlds exist, we now know they are abundant. Instead of imagining where life might be possible, we are identifying specific targets for observation. The question has shifted from whether planets exist to whether any of them contain life. Another important development in this search is the study of extreme life on Earth. Organisms known as extremophiles can survive in conditions once thought completely uninhabitable. Some live in deep ocean hydrothermal vents, where temperatures are extremely high and pressure is immense. Others survive in frozen environments, acidic lakes, or highly radioactive areas. These discoveries have expanded our understanding of what life can endure. The existence of extremophiles suggests that life may be far more adaptable than previously believed. If life can survive in such extreme conditions on Earth, it may also be able to exist in similarly extreme environments elsewhere in the universe. This has broadened the range of places considered potentially habitable. Moons in our own solar system have also become important targets in the search for life. Some of these moons, such as Europa and Enceladus, are believed to contain subsurface oceans beneath their icy crusts. These hidden oceans may be kept liquid by internal heating caused by gravitational interactions with their parent planets. If these environments contain energy sources and chemical ingredients, they could potentially support microbial life. The idea that life might exist beneath ice layers far from sunlight challenges traditional assumptions. It suggests that life does not necessarily require surface conditions similar to Earth. Instead, it may arise in hidden environments where energy and chemistry interact in unexpected ways. As our exploration of the universe continues, we are constantly expanding the definition of where life might exist. What began as a simple question about other planets has become a complex investigation involving chemistry, physics, geology, and biology. Each discovery adds a new piece to the puzzle, but also reveals how much more there is to understand. The search for extraterrestrial life is ultimately a search for context. It is an attempt to understand whether life on Earth is unique or part of a broader cosmic pattern. It is also a way of understanding our place in the universe. If life exists elsewhere, it would suggest that the conditions that led to our existence are not rare. If life is rare or unique, it would raise even deeper questions about how and why it emerged here. At this stage in our exploration, we do not yet have a definitive answer, but we do have tools, observations, and theories that allow us to explore the question in a meaningful way. We are no longer limited to speculation. We are conducting real searches, analyzing real data, and building real models of distant worlds. The universe is vast beyond comprehension. It contains billions of galaxies, each with billions of stars, many of which have their own planetary systems. Within this enormous structure, the possibility of life elsewhere cannot be ignored. Whether simple or complex, microbial or intelligent, the potential for life exists wherever the right conditions come together. And so the search continues, driven by curiosity, evidence, and the fundamental human desire to understand whether we are alone in the cosmos or part of something much larger. To understand the possibility of life beyond Earth, we must first understand what life actually needs in order to exist. This is not as simple as listing ingredients. Life is not just chemistry in motion. It is a process that depends on structure, energy, stability, and time. On Earth, life is built from a small set of chemical elements, but these elements must interact in very specific ways. The universe is filled with matter, yet only certain environments allow that matter to organize into something living. At the most basic level, life requires atoms that can form complex and stable molecules. Carbon is central to this process because of its unique ability to form long chains and rings with itself and with other elements. These structures are flexible, diverse, and stable enough to support the complexity needed for biological systems. Without carbon, life as we know it would not exist, but carbon alone is not enough. It must be combined with other elements in specific environments where chemical reactions can occur over long periods. Hydrogen and oxygen form water, one of the most important substances for life. Water is not just a solvent. It is a medium that allows molecules to move, collide, and react in ways that would not be possible in solid or gaseous environments alone. It stabilizes temperatures, transports nutrients, and provides a controlled environment for chemical processes. In many theories of life, water is considered essential because it creates the conditions for complexity to emerge. Nitrogen plays another critical role. It is a key component of amino acids and nucleic acids, the building blocks of proteins and genetic material. Without nitrogen, the structures that store and transmit biological information would not exist. Sulfur, phosphorus, and trace metals also contribute to biochemical systems, enabling reactions that support metabolism and energy transfer. What is striking is that all of these elements are not rare in the universe. They are produced inside stars through nuclear fusion and distributed across space by stellar winds and supernova explosions. This means that the raw materials for life are widespread. The universe is chemically prepared for complexity. The question is not whether the ingredients exist, but where and how they combine in the right conditions. Energy is another fundamental requirement for life. Biological systems need a constant flow of energy to maintain structure and drive chemical reactions. On Earth, this energy comes primarily from the sunday. Photosynthesis converts sunlight into chemical energy, which then supports food chains and ecosystems. But energy sources in the universe are not limited to stars. Chemical gradients, geothermal activity, and radioactive decay can also provide energy for biological processes. This expands the range of possible environments where life might exist. It means that life does not necessarily depend on sunlight. It only requires a stable and accessible energy source that can drive chemical reactions over long periods. In some environments, such as deep ocean hydrothermal vents, life on Earth already demonstrates this principle. There, organisms survive without sunlight, relying instead on chemical energy from the planet's interior. Stability is another key factor. Life requires environments that persist long enough for complex structures to form and evolve. If conditions change too rapidly, chemical systems cannot develop the complexity needed for biology. Stability does not mean permanence, but rather a balance where change occurs gradually enough for systems to adapt and grow. This is why planets are such important candidates for life. Planets provide long-term stability compared to many other environments in the universe. They orbit stars in predictable patterns, maintain gravitational balance, and can retain atmospheres and liquids over extended periods. These conditions create the possibility for chemical evolution to proceed over millions or billions of years. However, not all planets are suitable for life. Many are too hot, too cold, or lack the necessary chemical ingredients. Some have thick, toxic atmospheres or are constantly bombarded by radiation. Others may be geologically unstable or lack magnetic fields to protect their surfaces. The presence of a planet alone does not guarantee habitability. It is the combination of many factors that determines whether life can emerge. This is where the concept of the habitable zone becomes important. The habitable zone around a star is the region where temperatures allow liquid water to exist on a planet's surface. This idea is based on Earth, as an example, but it is not a strict boundary. Different types of stars have different habitable zones, and planets with unique atmospheres or internal heating may extend or shift these boundaries. For example, a planet slightly outside the traditional habitable zone might still support liquid water if it has a thick atmosphere that traps heat. Conversely, a planet within the habitable zone might be uninhabitable if it lacks an atmosphere or has extreme geological conditions. This shows that habitability is not defined by distance alone, but by a combination of physical and chemical properties. The discovery of exoplanets has shown that planetary systems are extremely diverse. Some planets are gas giants with no solid surface, while others are rocky worlds similar to Earth. Some orbit closely around small red dwarf stars, while others travel in wide orbits around larger stars. This diversity suggests that the universe contains many different environments where life might potentially arise. Red dwarf stars are particularly interesting in the search for life. They are smaller and cooler than stars like the Sun, which means their habitable zones are much closer in. Planets in these zones are often tidally locked, meaning one side always faces the star while the other remains in darkness. At first glance, this might seem hostile to life, but atmospheric circulation could distribute heat, creating stable regions where life might exist. This shows how flexible the concept of habitability can be. Life may not require Earth-like conditions. It may adapt to environments that are very different from our own. The more we study exoplanets, the more we realize that there may be many pathways to habitability, not just one. Another important factor is time. Life does not emerge instantly. It requires long periods for chemical systems to develop complexity. On Earth, life appeared relatively early in the planet's history, but it took billions of years to evolve into complex organisms. This suggests that even if conditions are right, time is still a limiting factor. Planets around long-lived stars may therefore be better candidates for life. Red dwarf stars, for example, can remain stable for trillions of years. This provides a very long window for life to potentially emerge and evolve. In contrast, massive stars have much shorter lifespans, which may not allow enough time for complex life to develop. In addition to planets, moons have also become important targets in the search for life. Some moons in our solar system, such as Europa and Enceladus, are believed to contain subsurface oceans beneath icy crusts. These oceans are kept liquid by tidal heating, caused by gravitational interactions with their parent planets. In these hidden environments, water, energy, and chemical compounds may exist together in stable conditions. If life exists in such environments, it would not rely on sunlight at all. Instead, it would depend on internal planetary energy sources. This expands the definition of habitability even further. It suggests that life could exist in hidden oceans far from the surface, protected from harsh radiation and extreme temperature changes. The idea of subsurface life challenges traditional assumptions about where life can exist. It shows that habitable environments may be more common than previously thought, simply because they do not always need to be visible from space. They can exist beneath ice, rock, or other protective layers. As we combine all these factors, chemical building blocks, energy sources, stability, and time, we begin to see a broader picture of habitability in the universe. Life is not tied to a single type of environment. Instead, it is a process that can potentially arise in many different settings as long as the right conditions align. This leads to a profound realization. The universe is not just a collection of stars and planets. It is a system filled with potential environments for life. Some of these environments may be similar to Earth. Others may be completely different, operating under conditions we are only beginning to understand. The search for extraterrestrial life is therefore not just about finding another Earth. It is about understanding the full range of possibilities that nature allows. It is about exploring how chemistry, physics, and time interact to create complexity. Every new discovery of a planet, every detection of water or organic molecules, and every study of extreme environments on Earth adds to this understanding. We are slowly mapping the conditions under which life can exist, both here and elsewhere in the universe. And with each step forward, the question becomes less about whether life is possible beyond Earth, and more about where and how it might already exist. When we think about where life might exist in the universe, one of the first ideas that emerges is the concept of distance from a star. A planet cannot be too close or too far from its star if it is to maintain conditions suitable for liquid water on its surface. This idea forms the basis of what scientists call the habitable zone, a region around a star where temperatures may allow water to remain in liquid form over long periods of time. This simple concept has become one of the most important tools in the search for extraterrestrial life. The idea of a habitable zone is rooted in Earth's position in the solar system. Earth orbits the Sun at a distance where temperatures are stable enough for water to exist in all three states: solid, liquid, and gas. This balance allows oceans to form, atmospheres to develop, and climate systems to stabilize over geological timescales. Without this balance, life as we know it would not be possible. If Earth were closer to the Sun, oceans would evaporate. If it were farther away, they would freeze. The narrow range where conditions are just right is what makes Earth uniquely suitable for life. When scientists began to apply this idea to other stars, they realized that habitable zones are not fixed or universal. They depend on the type of star. Hotter, more massive stars have habitable zones that are farther away, while cooler, smaller stars have habitable zones that are much closer in. This means that the location of potentially habitable planets varies depending on the nature of the star they orbit. However, distance alone does not determine habitability. A planet within the habitable zone may still be uninhabitable if other conditions are not suitable. For example, if a planet has no atmosphere, it cannot retain heat or support stable liquid water. If it has a thick, toxic atmosphere, surface conditions may be too extreme for life. If it is geologically inactive or lacks essential chemical elements, it may also be unable to support biological processes. The habitable zone is therefore only a starting point, not a guarantee. Despite its limitations, the habitable zone concept has been extremely useful in guiding the search for exoplanets. When astronomers detect new planets around distant stars, they often check whether those planets lie within this zone. This helps prioritize targets for further study, especially when looking for signs of liquid water or atmospheric conditions that could support life. One of the most important discoveries in modern astronomy is that planets are extremely common. Almost every star in the galaxy is now believed to have at least one planet orbiting it. Many stars have entire systems of planets, just like our solar system. This means that there are billions of planets in our galaxy alone and potentially trillions across the observable universe. Among these vast numbers, even a small fraction of habitable worlds would represent an enormous number of potential environments for life. The discovery of exoplanets has also revealed that planetary systems can be very different from our own. Some systems contain giant planets orbiting very close to their stars, known as hot Jupiters. Others contain tightly packed systems of small rocky planets. Some planets have highly elliptical orbits that take them in and out of their star's habitable zone. This diversity suggests that the conditions for habitability may arise in many different ways, not just in Earth-like configurations. Red dwarf stars have become particularly important in this search. These stars are smaller and cooler than the Sun, but they are also the most common type of star in the galaxy. Because they are so numerous, they represent a large portion of potential habitable environments. Their habitable zones are much closer to the star, meaning that planets in these regions often orbit very tightly. This close orbit creates unique challenges. Planets in the habitable zone of red dwarfs are often tidally locked, meaning one side always faces the star while the other remains in darkness. This creates extreme temperature differences between the two sides. However, atmospheric and oceanic circulation could potentially distribute heat across the planet, creating more stable regions where life might exist. This shows that even seemingly extreme conditions may still allow for habitability under the right circumstances. Another challenge for planets around red dwarfs is stellar activity. These stars can produce powerful flares and bursts of radiation that might strip away atmospheres or damage biological molecules. However, a thick atmosphere or strong magnetic field could provide protection. Life, if it exists in such environments, may need to adapt to high levels of radiation or find refuge in protected regions such as underground or underwater habitats. In addition to planets around stars, scientists have also considered other types of habitable environments. One of the most promising are icy moons that orbit planets in our own solar system. Moons such as Europa and Enceladus are believed to contain vast oceans beneath their icy surfaces. These oceans are kept liquid by tidal heating, which is caused by gravitational interactions with their parent planets. These subsurface oceans are particularly interesting because they are protected from the harsh conditions of space. They are shielded from radiation and temperature extremes by thick layers of ice. If these oceans contain chemical energy sources, such as hydrothermal vents on the ocean floor, they could provide environments suitable for microbial life. The idea of subsurface habitability expands the search for life beyond surface conditions. It suggests that life does not necessarily need sunlight or Earth-like environments. Instead, it may thrive in hidden ecosystems powered by internal planetary energy sources. This greatly increases the number of potential habitats in the universe. Another important factor in habitability is planetary atmosphere. An atmosphere plays a crucial role in regulating temperature, protecting the surface from radiation, and enabling chemical cycles. Without an atmosphere, a planet is exposed to extreme temperature variations and harmful radiation from space. With a suitable atmosphere, a planet can maintain stable conditions over long periods. The composition of an atmosphere also matters. Gases such as carbon dioxide, nitrogen, and water vapor can support different types of climate systems. The presence of oxygen, while important for complex life on Earth, is not necessarily required for all forms of life. In fact, early life on Earth existed without oxygen for billions of years. This suggests that the search for life should not focus only on Earth-like conditions. Instead, it should consider a wide range of possible atmospheric compositions and chemical environments. Life may adapt to conditions very different from those found on Earth, especially if it arises through different chemical pathways. Temperature stability is another key factor. Life requires environments where temperatures do not fluctuate too rapidly or exceed certain limits. Stable temperatures allow chemical reactions to proceed in controlled ways, supporting the development of complex molecules. Planets with stable orbits, thick atmospheres, or large bodies of water are more likely to maintain such conditions. Time also plays a critical role in habitability. Even if a planet has the right conditions, life may take a long time to emerge. On Earth, it took hundreds of millions of years for life to appear after the planet formed, and billions of years for complex life to evolve. This means that long-term stability is essential for life to develop beyond simple forms. Stars with long lifespans provide more time for this process. Small, stable stars can remain active for billions or even trillions of years. This gives planets around them a long window of opportunity for life to emerge and evolve. In contrast, large stars burn out quickly, reducing the time available for biological development. The combination of these factors, distance from a star, atmospheric composition, planetary structure, energy sources, and time, creates a complex picture of habitability. There is no single definition of a habitable world. Instead, there are many possible pathways to environments that could support life. As our understanding of these factors improves, the search for extraterrestrial life becomes more focused. Scientists can now identify specific planets and moons that meet multiple criteria for habitability. They can study atmospheres, analyze chemical signatures, and look for signs of water and energy. Despite all this progress, we still do not know whether life exists beyond Earth. But what we do know is that the number of potentially habitable environments in the universe is far greater than once imagined. The conditions for life are not rare in a strict sense. They may arise in many different forms across many different systems. This realization shifts the question from whether life is possible to how often it might occur. It opens the door to a universe filled with potential, where life may exist in forms and environments we have not yet fully imagined. And so, the habitable zone is not just a region around a star. It is a concept that helps us understand the balance of conditions required for life. It is a guide in our search, but also a reminder that the universe is vast, diverse, and still largely unexplored. For most of human history, planets beyond our solar system were only theoretical. We knew that stars were distant suns, and many thinkers suspected they might have their own worlds, but there was no way to confirm it. The universe beyond our solar system was a blank canvas, filled with possibility but no direct evidence. That changed when technology reached a point where we could finally begin to detect planets orbiting other stars. These worlds are known as exoplanets, and their discovery transformed the search for extraterrestrial life from speculation into observation. The first confirmed detection of an exoplanet marked a turning point in astronomy. Until then, our solar system was the only example we had of planetary systems. We assumed that other systems might look similar, with small rocky planets near the star and larger gas giants farther out. But as more exoplanets were discovered, it became clear that planetary systems are far more diverse than we ever imagined. One of the most important methods used to detect exoplanets is the transit method. This technique involves observing a star's light over time and looking for small dips in brightness. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the light. This creates a regular pattern in the star's brightness that can reveal the presence of a planet. By measuring the size and timing of these dips, scientists can determine the planet's size, orbit, and sometimes even aspects of its atmosphere. Another method is the radial velocity technique, which measures the tiny wobble of a star caused by the gravitational pull of an orbiting planet. Even though planets are much smaller than stars, their gravity still affects the star's motion. By analyzing changes in the star's light spectrum, scientists can detect this wobble and infer the presence of a planet. This method was crucial in the early discovery of exoplanets and remains an important tool today. As detection methods improved, the number of known exoplanets began to grow rapidly. What started as a handful of discoveries turned into thousands within a few decades. Each new discovery revealed something unexpected. Some planets were much larger than Jupiter, but orbiting extremely close to their stars. Others were rocky worlds much larger than Earth, known as super-Earths. Some systems contained multiple planets packed into tight orbital configurations, unlike anything seen in our own solar system. This diversity challenged long-held assumptions about how planetary systems form. It showed that the processes that create planets are flexible and complex. The distribution of planets depends on many factors, including the composition of the protoplanetary disk, the presence of nearby stars, and the dynamics of gas and dust during formation. Among the most exciting discoveries are Earth-like planets, worlds that are similar in size and composition to our own. These planets are of particular interest because they may have solid surfaces, atmospheres, and potentially liquid water. Some of them orbit within the habitable zones of their stars, making them strong candidates in the search for life. However, identifying an Earth-like planet does not guarantee habitability. Many factors must align for a planet to support life. Its atmosphere must be stable, its temperature must allow liquid water, and its chemical composition must include the necessary building blocks for biology. Even then, we do not yet know how often life actually emerges under such conditions. One of the most important discoveries in exoplanet research is that planets are incredibly common. It now appears that most stars in the galaxy have at least one planet, and many have multiple. This means that there are billions of planets in our galaxy alone. When multiplied across the observable universe, the number becomes almost incomprehensible. Among these vast numbers, even rare conditions for life could still exist many times over. Some of the most intriguing exoplanets are those that do not fit neatly into categories found in our solar system. Super-Earths, for example, are planets larger than Earth but smaller than Neptune. They may have rocky surfaces, deep oceans, or thick atmospheres. We do not yet fully understand what these worlds are like, but they may represent a common type of planet in the universe. Another interesting class of planets are mini-Neptunes, which are smaller than Neptune but still have thick gaseous atmospheres. These planets likely do not have solid surfaces in the traditional sense, but they may contain layers where pressure and temperature create unusual chemical environments. While they may not be suitable for life as we know it, they expand our understanding of planetary diversity. Hot Jupiters are another surprising discovery. These are gas giant planets that orbit extremely close to their stars, sometimes completing an orbit in just a few days. Their existence challenged early models of planetary formation, which suggested that gas giants should form far from their stars. Their presence shows that planets can migrate over time, moving through their systems in complex ways. The study of exoplanet atmospheres has become one of the most important areas in modern astronomy. By analyzing the light that passes through a planet's atmosphere during a transit, scientists can identify the chemical composition of that atmosphere. This technique has already revealed the presence of water vapor, carbon dioxide, methane, and other molecules on distant worlds. These chemical signatures are particularly important because they may indicate processes related to life. On Earth, certain combinations of gases are maintained by biological activity. If similar patterns are found on other planets, they could suggest the presence of life, although alternative, non-biological explanations must always be considered. The detection of exoplanets has also led to the identification of potentially habitable candidates. These are planets that meet several key criteria, such as being located within the habitable zone and having a size similar to Earth. Some of these planets orbit nearby stars, making them important targets for future observation. One of the most famous examples is a system of multiple Earth-sized planets orbiting a small red dwarf star. Several of these planets lie within the star's habitable zone, raising the possibility that they could have liquid water. Although we do not yet know whether they are truly habitable, they represent some of the most promising candidates in the search for life. As technology continues to improve, our ability to study exoplanets is becoming more detailed. New telescopes are being designed to analyze atmospheric composition with greater precision. Future missions will focus on detecting biosignatures, chemical patterns that could indicate biological activity. However, interpreting these signals is extremely complex. Many processes in nature can produce similar chemical signatures. For example, methane can be produced by both biological and geological processes. Oxygen can accumulate in an atmosphere through non-biological means under certain conditions. This makes it difficult to distinguish between life and non-life based on chemistry alone. Despite these challenges, the search continues to move forward. Each new discovery brings us closer to understanding the true nature of planetary systems and the potential for life beyond Earth. We are gradually building a map of the galaxy, identifying worlds that could harbor conditions suitable for biology. One of the most profound implications of exoplanet research is the realization that Earth is not unique in its structure. There are many planets that share similar characteristics. While this does not prove that life exists elsewhere, it suggests that the conditions that made life possible on Earth are not singular or rare. This leads to a deeper question. If the universe is filled with planets that could support life, then where is it? This question becomes even more powerful as we discover more and more potentially habitable worlds. It sets the stage for further exploration into the possibility of intelligent civilizations, communication across interstellar distances, and the search for signals that might indicate technology beyond Earth. For now, exoplanets represent one of the most important frontiers in science. They are not just distant worlds, they are laboratories for understanding how planets form, evolve, and potentially support life. Each one adds a new piece to the puzzle of the universe. And as we continue to discover them, we are forced to reconsider our place in the cosmos. We are no longer confined to a single planetary system. We are part of a galaxy filled with countless worlds, each with its own story, its own history, and possibly its own form of life waiting to be discovered. For centuries, the search for life beyond Earth focused almost entirely on distant worlds. on planets orbiting other stars, and on the vast unknown regions of space that might contain environments similar to our own. But as our understanding of life deepened, a surprising realization emerged. If we want to understand where life might exist elsewhere, we do not need to look only outward. We can also look inward, to Earth itself, to the extreme environments where life already thrives under conditions once thought impossible. These organisms are known as extremophiles, and they have completely changed our understanding of what life can endure. Extremophiles are organisms that live in environments that would be lethal to most known life forms. They survive in extreme heat, extreme cold, intense pressure, high radiation, acidic conditions, and even in complete darkness without sunlight. At first glance, these environments seem completely uninhabitable. Yet life not only exists there, it thrives. This discovery has forced scientists to rethink the limits of biology and expand the definition of habitability far beyond traditional expectations. One of the most striking examples of extremophiles can be found in deep ocean hydrothermal vents. These vents are located on the ocean floor, where tectonic activity allows superheated water to escape from beneath the Earth's crust. The temperature near these vents can reach levels that would normally destroy biological molecules. The pressure is also extreme due to the weight of the ocean above. Yet, in these harsh conditions, entire ecosystems exist. Instead of relying on sunlight, these ecosystems are powered by chemical energy. Certain microorganisms, known as chemosynthetic bacteria, convert chemicals like hydrogen sulfide into usable energy. These bacteria form the base of a food chain that supports a variety of life forms, including tube worms, crustaceans, and other specialized organisms. This discovery was groundbreaking because it showed that life does not require sunlight to exist. It only requires a source of energy, even if that energy comes from chemical reactions deep beneath the surface of a planet. This finding has enormous implications for the search for life beyond Earth. If life can exist in complete darkness on Earth, then similar environments on other worlds could potentially support life as well. Moons like Europa and Enceladus, which contain subsurface oceans beneath icy crusts, become even more interesting in this context. If hydrothermal activity exists beneath their oceans, they could provide the same kind of chemical energy that supports life in Earth's deep seas. Another extreme environment where life thrives is in volcanic regions. Some microorganisms live in boiling hot springs and acidic pools where temperatures are close to or even above the boiling point of water. These organisms, known as thermophiles and hyperthermophiles, have adapted to survive at temperatures that would destroy most biological systems. Their enzymes and cellular structures are specially designed to remain stable under extreme heat. These organisms suggest that temperature limits for life may be far broader than previously thought. While most life on Earth exists within a relatively narrow temperature range, extremophiles demonstrate that biology can adapt to conditions far outside this range. This raises the possibility that life elsewhere in the universe might also exist in environments that would seem hostile from an Earth-centered perspective. Cold environments also support life. In Antarctica, microorganisms survive in sub-zero temperatures beneath ice sheets and within frozen soil. Some bacteria remain active in ice cores that are hundreds of thousands of years old. These cold-adapted organisms, known as psychrophiles, show that life can function even when temperatures are extremely low. They achieve this through specialized proteins and cellular mechanisms that prevent freezing damage and maintain metabolic activity at very low energy levels. The existence of psychrophiles is particularly relevant when considering icy worlds in the outer solar system. Planets and moons with frozen surfaces may still contain liquid water beneath their ice layers where temperatures are more stable. If life can persist in cold environments on Earth, it strengthens the possibility that similar life forms could exist in these distant icy regions. Another extreme condition that life can tolerate is high radiation. Certain microorganisms have been discovered that can survive intense levels of radiation that would be lethal to most known organisms. These radiation-resistant extremophiles have evolved mechanisms to repair damaged DNA and protect their cellular structures. One well-known example is a bacterium that can survive exposure to radiation levels thousands of times higher than what would kill a human. This ability has important implications for space environments. Many regions of space are filled with high levels of radiation from stars and cosmic sources. Planets without strong magnetic fields or thick atmospheres are exposed to this radiation constantly. Yet, if life can survive extreme radiation on Earth, it suggests that radiation alone may not be a complete barrier to life elsewhere. Some extremophiles thrive in highly acidic or alkaline environments. Acidic lakes, for example, can have pH levels that would dissolve most biological tissues. Yet, specialized microorganisms have adapted to live in these conditions by maintaining internal stability and protecting their cellular structures. Similarly, alkaline environments with extremely high pH values also support unique forms of microbial life. These adaptations demonstrate that life is not limited to neutral environments. It can evolve mechanisms to survive in highly chemically reactive conditions. This expands the range of possible habitats where life might exist beyond Earth. Pressure is another extreme condition that life can endure. In the deepest parts of the ocean, pressure is so intense that it would crush most organisms instantly. Yet even in these environments, life exists. Deep-sea organisms have adapted to withstand immense pressure, often using flexible cellular structures and specialized biochemical systems that function under compression. This is particularly relevant when considering subsurface oceans on other worlds. If life can survive under extreme pressure on Earth, it may also be able to survive in the deep oceans of icy moons or in other high-pressure environments throughout the universe. Perhaps one of the most important insights from the study of extremophiles is that life is fundamentally adaptable. It does not require a single set of conditions. Instead, it can evolve to fit a wide range of environments. This adaptability suggests that life may be far more common in the universe than previously thought, because it is not restricted to narrow conditions. Extremophiles also provide clues about the origins of life on Earth. Early Earth was a much more hostile environment than it is today. Volcanic activity was more intense, radiation levels were higher, and atmospheric conditions were very different. It is possible that early life began in extreme environments similar to those where extremophiles are found today. If this is true, then extremophiles are not just survivors of harsh conditions, but possibly living examples of ancient life strategies. This connection between extremophiles and the origin of life is important for astrobiology. It suggests that life elsewhere might also begin in extreme environments and later adapt to more stable conditions. Instead of requiring Earth-like conditions from the start, life may begin in environments that seem hostile but are actually chemically and energetically rich. As scientists study extremophiles, they are also developing new models for where to search for life beyond Earth. Instead of focusing only on planets within habitable zones, they now consider a wider range of environments. Subsurface oceans, geothermal systems, and chemically active regions are all potential targets. This broader perspective increases the number of possible habitats in the universe significantly. It suggests that life may not be rare, but simply distributed across a wider variety of environments than previously imagined. The universe may contain many forms of life, adapted to conditions that are very different from those on Earth. Extremophiles also challenge our assumptions about intelligence and complexity. While most known extremophiles are simple microorganisms, their existence raises the question of whether more complex life could also adapt to extreme environments. If simple life can survive in such a wide range of conditions, it is possible that more complex systems could evolve under similarly diverse circumstances elsewhere in the universe. The study of extremophiles is therefore not just about understanding life on Earth. It is about expanding the boundaries of what we consider possible. Every discovery of life in extreme conditions pushes those boundaries further outward, suggesting that the limits of biology are not fixed, but flexible. In the context of the search for extraterrestrial life, extremophiles serve as a bridge between Earth and the rest of the universe. They show that life does not require perfect conditions. It only requires conditions that allow chemistry and energy to interact in stable and sustained ways. These conditions may exist in many places beyond Earth, even in environments that initially appear completely uninhabitable. As we continue to explore the universe, extremophiles remind us that life is resilient, adaptable, and persistent. It can survive in darkness, heat, cold, radiation, pressure, and chemical extremes. This resilience suggests that if life exists elsewhere in the universe, it may be far more widespread and diverse than we currently imagine. And so, by studying life in its most extreme forms on Earth, we are not just learning about survival, we are learning about possibility. We are learning that the universe may be far more alive in far more places than we ever thought before. When we search for life beyond Earth, we often begin by focusing on planets that resemble our own. We imagine rocky surfaces, breathable atmospheres, and liquid water flowing across open landscapes. But the universe does not always follow the patterns we expect. Some of the most promising places to find life may not be planets at all. They may be moons, hidden in the shadows of giant planets, far from direct sunlight, where conditions appear frozen and lifeless on the surface. Beneath that frozen exterior, however, entire oceans may exist, sealed away from space and warmed from within. These are the icy moons, and they have become some of the most intriguing candidates in the search for extraterrestrial life. In our solar system, two moons stand out as particularly important in this context: Europa and Enceladus. These worlds orbit giant planets, Jupiter and Saturn, and are covered in thick layers of ice. At first glance, they appear to be among the least hospitable places in the solar system. Their surfaces are cold, dark, and bombarded by radiation from their parent planets. There is no atmosphere like Earth's, no visible liquid water, and no obvious signs of life. Yet beneath their icy crusts, something remarkable may be happening. Scientists believe that both Europa and Enceladus contain vast subsurface oceans of liquid water. These oceans are not frozen solid because of a process known as tidal heating. As these moons orbit their massive planets, gravitational forces constantly stretch and compress their interiors. This creates friction and generates heat deep within the moons, keeping water in a liquid state beneath the surface ice. In Europa's case, this ocean may be tens of kilometers deep, containing more water than all of Earth's oceans combined. The idea of a hidden ocean beneath an icy shell changes everything about how we think life might exist in the universe. On Earth, life is concentrated in environments where sunlight is available or where surface conditions are stable. But in these icy moons, life would have to exist completely out of sight, in darkness, beneath kilometers of ice. This means that if life exists there, it would be independent of sunlight entirely, relying instead on internal energy sources. One of the most important questions in astrobiology is whether energy is available in these subsurface oceans. On Earth, life requires energy to survive and grow. In the deep ocean, near hydrothermal vents, this energy comes from chemical reactions between water and minerals from the ocean floor. If similar processes occur on Europa or Enceladus, they could provide a continuous energy source for potential life. Evidence for such processes is especially strong in Enceladus. Space missions have observed plumes of water vapor and ice particles erupting from fractures in its icy surface. These plumes contain organic molecules, salts, and other chemical compounds that suggest interaction between the subsurface ocean and a rocky interior. This indicates that hydrothermal activity may exist beneath the ice, creating conditions that could support life. Europa also shows signs of a dynamic subsurface environment. Its surface is marked by cracks, ridges, and chaotic regions that suggest movement and interaction between the ice and the ocean below. Magnetic field measurements from spacecraft have also provided evidence of a conductive layer beneath the surface, consistent with a salty liquid ocean. If these oceans exist, they would be completely isolated from the surface environment. This isolation could actually be beneficial for life. On Earth, surface life is exposed to radiation, temperature fluctuations, and other environmental stresses. In contrast, a subsurface ocean would provide a stable environment protected from external hazards. The ice layer above would act as a shield, preserving conditions suitable for life over long periods of time. In such an environment, life would likely be microbial rather than complex. It would exist in forms similar to bacteria or archaea on Earth, adapted to dark, cold, and chemically rich conditions. These organisms would not rely on sunlight. Instead, they would use chemical energy derived from interactions between water, rock, and dissolved compounds. This type of life is known as chemosynthetic life, and it already exists on Earth in deep ocean environments. At hydrothermal vents on the seafloor, ecosystems thrive without any sunlight at all. Instead, bacteria use chemical reactions involving hydrogen sulfide and other compounds to produce energy. These bacteria form the base of a food chain that supports more complex organisms. If similar systems exist on icy moons, they could potentially support entire ecosystems beneath the ice. The possibility of life in subsurface oceans raises important questions about how life begins and evolves. On Earth, life is thought to have originated in water, possibly in environments similar to hydrothermal vents. If this is true, then icy moons with subsurface oceans may provide similar conditions for the origin of life elsewhere in the universe. Unlike surface planets, these environments are shielded from harsh radiation and meteor impacts. This stability could allow chemical processes to continue uninterrupted for long periods of time. Over millions or billions of years, simple molecules could gradually become more complex, eventually leading to self-sustaining biological systems. Another important factor is the chemical composition of these oceans. Water alone is not enough for life. It must be combined with other elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are believed to exist within icy moons, delivered through meteoritic material or formed through internal geological processes. If the right chemical balance exists, it could create an environment capable of supporting life. Energy sources in these environments are also diverse. In addition to hydrothermal activity, chemical gradients between different layers of the ocean could provide energy for biological processes. Salinity differences, pressure variations, and mineral interactions could all contribute to creating conditions where chemical reactions drive metabolism. One of the most fascinating aspects of icy moon habitability is that it does not depend on distance from the sunday. Unlike traditional habitable zones, which are based on surface temperature and solar energy, subsurface oceans rely on internal heating. This means that even moons far from the sun can potentially support life if they have enough internal energy. This significantly expands the range of environments considered habitable. It suggests that life could exist in places that would normally be dismissed as too cold or too dark. It also means that moons orbiting giant planets throughout the galaxy could represent a vast and previously underestimated category of potentially habitable worlds. Exploring these environments is extremely challenging. Thick layers of ice make direct observation of subsurface oceans difficult. Space missions must rely on indirect measurements, such as gravitational fields, magnetic signatures, and surface features. Future missions may attempt to drill through ice or use robotic probes to explore beneath the surface. But these technologies are still in development. Despite these challenges, the scientific interest in icy moons continues to grow. They represent some of the most accessible potential habitats for life beyond Earth. Unlike distant exoplanets, they are within our own solar system, making them realistic targets for exploration in the near future. If life is discovered in one of these subsurface oceans, it would have profound implications. It would suggest that life can arise independently in multiple environments within a single solar system. This would greatly increase the likelihood that life exists elsewhere in the universe. It would also suggest that the conditions for life are not as rare or specific as once thought. Even if no life is found, studying these environments will still provide valuable information. It will help us understand the limits of habitability, the role of internal heating in planetary systems, and the range of chemical processes that occur in extreme environments. This knowledge will improve our ability to identify promising targets in the search for life beyond our solar system. Icy moons also highlight an important idea in astrobiology. Life does not need to be visible from space to exist. It can be hidden beneath surfaces, protected from harsh environments, and sustained by internal energy sources. This means that the absence of visible signs does not necessarily mean the absence of life. As we continue to explore the solar system, icy moons remind us that life may exist in places we have not yet fully considered. They expand our imagination and challenge our assumptions about where life can exist. They show that even in the coldest, darkest regions of space, there may be environments capable of supporting complex chemistry and possibly biology. In the broader search for extraterrestrial life, icy moons represent a shift in perspective. They move the focus away from surface conditions and toward hidden environments. They suggest that life may be more common in subsurface oceans than on open planetary surfaces, and they remind us that the universe still holds many secrets beneath layers we have not yet been able to explore. And so, beneath the frozen shells of distant moons, entire oceans may be waiting. Silent, hidden, and unexplored, they may contain the conditions necessary for life to emerge, persist, and perhaps even evolve in ways we have yet to imagine. When scientists try to estimate how many intelligent civilizations might exist in the universe, they quickly run into a problem. We only have one confirmed example of life that has developed intelligence and technology, and that is Earth. With a sample size of 1, it becomes extremely difficult to make reliable statistical predictions about how common intelligent life might be elsewhere. Yet, despite this limitation, researchers have developed frameworks to guide the discussion, and one of the most famous of these is the Drake equation. The Drake equation is not a single answer. It is a structured way of thinking about the variables that might influence the number of communicative civilizations in our galaxy. It breaks the problem into a series of factors, each representing a step in the progression from stars to intelligent life. By estimating each factor, scientists can explore a range of possibilities, from a galaxy filled with civilizations to one where Earth is the only example. The first factor in the equation is the rate of star formation in our galaxy. This represents how many new stars are born each year. Stars are the foundation of planetary systems, so without stars, there would be no planets and no potential habitats for life. The Milky Way is a dynamic system where stars are constantly forming from clouds of gas and dust. Although the rate of star formation varies over time, it provides the raw material for all future possibilities of life. The second factor is the fraction of those stars that have planetary systems. For a long time, it was uncertain whether planets were common or rare. But modern observations have shown that planets are extremely widespread. Most stars appear to host at least one planet, and many have multiple. This dramatically increases the number of potential environments where life could exist. The third factor is the number of planets per system that could potentially support life. This depends on many conditions, including distance from the star, planetary composition, atmosphere, and stability. Some systems may have multiple habitable worlds, while others may have none. Even within a single system, conditions can vary widely from one planet to another. The fourth factor is the fraction of habitable planets where life actually arises. This is one of the greatest unknowns in science. We do not yet know how easily life begins. On Earth, life appeared relatively early in the planet's history, which might suggest that life is common under the right conditions. But this is based on a single example, so it is impossible to draw firm conclusions. Life could be easy to start, or it could be extremely rare. The fifth factor is the fraction of life-bearing planets where intelligent life evolves. On Earth, life existed for billions of years before complex intelligence appeared. Most species that have ever lived were not intelligent in the technological sense. This suggests that intelligence may be a rare evolutionary outcome depending on many unpredictable factors such as environmental stability, competition, and chance events. The sixth factor is the fraction of intelligent civilizations that develop detectable technology. Intelligence alone does not guarantee technological development. A species must also develop communication systems, energy control, and tools that produce detectable signals. On Earth, this happened only very recently in evolutionary terms. It is possible that many intelligent species never develop technology at all. The final factor is the length of time such civilizations release detectable signals into space. Even if civilizations arise, they may not last long in a technological sense. They could self-destruct, lose interest in communication, or transition into forms of existence that are not detectable from a distance. The duration of a civilization's technological phase has a major impact on how many we might detect at any given time. When all these factors are combined, the result can vary dramatically. Some estimates suggest that there could be many civilizations in the Milky Way. Others suggest that we might be alone or nearly alone. The uncertainty in each factor makes the final result highly sensitive to assumptions. This is why the Drake equation is often used more as a thought experiment than a precise calculation. Despite its uncertainty, the equation is valuable because it structures the problem. Instead of asking a vague question about alien life, it breaks the problem into measurable components. Each factor can be studied independently, using astronomy, biology, chemistry, and evolutionary theory. As our knowledge improves, we can refine each term and improve our overall understanding. One of the most important insights from this framework is that the existence of intelligent life depends on a long chain of unlikely events. Stars must form, planets must develop, conditions must remain stable, life must emerge, and intelligence must evolve. Each step in this chain adds a layer of complexity and uncertainty. However, the sheer scale of the universe changes the perspective. Even if each step is rare, the number of opportunities is enormous. There are hundreds of billions of stars in our galaxy alone, and billions of galaxies in the observable universe. This means that even extremely unlikely events could still occur many times over. This balance between rarity and scale is at the heart of the search for extraterrestrial intelligence. It is possible that intelligent life is rare but widespread due to the vast number of opportunities. It is also possible that one or more of the steps in the chain is extremely unlikely, making intelligent life extremely rare overall. Another important concept related to the Drake equation is the idea of observational bias. We are limited to observing the universe from a single point in space and time. This means that our sample is not random or representative. We see the universe as it is now, but also as it was in the past, due to the time it takes for light to travel across space. This makes it difficult to draw conclusions about the overall distribution of civilizations. Even if civilizations exist elsewhere, they may not overlap in time with our own. A civilization might rise and fall millions of years before or after we exist. Given the vast timescales of cosmic evolution, the probability of two civilizations existing at the same time and being close enough to detect each other may be very small. This leads to one of the most profound implications of the Drake equation. The universe may contain many civilizations, but they may be separated by time and distance in such a way that communication is extremely unlikely. This does not mean they do not exist. It simply means that the conditions for contact are rare. The equation also highlights the importance of longevity. Civilizations that survive for long periods of time have a higher chance of being detected. If a civilization lasts only a few thousand years, it may pass through a short technological phase and then disappear. If it lasts for millions of years, it has a much greater chance of interacting with others. This raises questions about the future of intelligent life. On Earth, we are currently in the early stages of technological development. Our ability to communicate across interstellar distances is limited, but it is rapidly improving. If civilizations can survive long enough to develop advanced technology, they may eventually become detectable across vast distances. The Drake equation also connects directly to the search for technosignatures. These are signs of technology that might be detectable from other star systems. Examples include radio signals, laser emissions, large-scale energy usage, or artificial structures that modify a star's light. Searching for these signatures is one of the primary goals of programs like SETI, the Search for Extraterrestrial Intelligence. So far, no confirmed technosignatures have been detected. However, this does not necessarily mean that intelligent civilizations do not exist. It may simply mean that they are rare, far away, or not using technologies that we can currently detect. As technology improves, our ability to search for these signals will also improve. New telescopes and instruments will allow us to scan larger portions of the sky with greater sensitivity. We may eventually be able to detect faint or indirect signs of technological activity on distant planets. The Drake equation continues to serve as a guiding framework for these efforts. It reminds us that the question of intelligent life is not a single problem, but a chain of interconnected factors. It also emphasizes the importance of each stage in the development of life, from star formation to technological civilization. In the end, the equation does not give us a final answer. Instead, it gives us a way to think about the problem systematically. It helps us understand where our knowledge is strong and where it is still uncertain. And it shows us that the question of whether we are alone in the universe is not just about discovery, but about understanding the conditions that make discovery possible. And so, the search continues, guided by probability, observation, and the deep curiosity that drives us to ask whether we are truly alone or just one example among many in a vast and evolving universe. If intelligent civilizations exist beyond Earth, one of the most natural questions that follows is how we might detect them. Unlike microbial life, which might only be detectable through chemical signatures or indirect evidence, advanced civilizations could potentially create signals that travel across interstellar space. These signals could take many forms, but one of the earliest and most widely studied possibilities is radio communication. This idea forms the foundation of the search for extraterrestrial intelligence, often referred to as SETI. Radio waves are a natural choice for interstellar communication because they can travel vast distances through space with relatively little interference. Unlike visible light, which can be blocked or scattered by dust, radio waves can pass through large regions of space and carry information over long distances. On Earth, we have used radio technology for over a century, unintentionally sending signals into space that have gradually expanded outward in a growing sphere. If another civilization had similar technology, their signals might also be traveling through the galaxy. The SETI program was built on the idea that if intelligent life exists elsewhere, it might use similar methods of communication. Early efforts focused on scanning the sky for narrow-band radio signals, which are unlikely to occur naturally. A narrowband signal is concentrated at a very specific frequency, making it stand out from the background noise of cosmic radiation. Such signals could indicate artificial origin, especially if they show patterns or repetition. One of the most famous early SETI efforts was the search for a signal known as the WOW signal. This was a strong, narrowband radio signal detected in 1977 that lasted for a short period and has never been observed again. Its origin remains unknown, and it continues to be one of the most intriguing unexplained detections in the history of radio astronomy. While it has not been confirmed as evidence of extraterrestrial intelligence, it demonstrated that unusual signals can and do appear in the data. Modern SETI efforts have become far more advanced. Instead of focusing on a single point in the sky, scientists now scan large regions using powerful radio telescopes and sophisticated algorithms. These systems can process enormous amounts of data, searching for patterns that might indicate artificial origin. Machine learning techniques are also being used to identify anomalies that might otherwise be missed. Despite decades of searching, no confirmed artificial signals have been detected. This absence of evidence has led to many questions. If intelligent civilizations are common, why have we not detected any signals? If they exist, are they not using radio technology, or are they deliberately avoiding detection? These questions have no clear answers, but they form part of a larger puzzle in understanding our place in the universe. One possible explanation is that civilizations may not use radio communication for long periods of time. On Earth, our use of radio technology is still relatively recent in cosmic terms. It is possible that civilizations transition to other forms of communication that are harder to detect or do not leak into space. For example, they might use tightly focused laser communication or advanced quantum systems that do not produce large-scale emissions. Another possibility is that civilizations may intentionally avoid broadcasting their presence. This idea is related to the concept of the cosmic silence, the apparent absence of detectable signals from other civilizations. Some theories suggest that civilizations may choose to remain quiet in order to avoid potential risks from unknown cosmic actors. While this is speculative, it highlights the range of possibilities when interpreting the lack of signals. In addition to radio waves, SETI research has expanded to include other types of technosignatures. A technosignature is any observable evidence of advanced technology, not limited to communication signals. This can include waste heat from large energy consumption, artificial structures that alter a star's light, or unusual atmospheric compositions on distant planets. One example of a potential technosignature is the search for Dyson spheres, hypothetical megastructures that might surround a star to capture its energy. While no such structures have been detected, the idea illustrates the types of large-scale engineering projects that advanced civilizations might undertake. If such structures existed, they could potentially alter the way a star appears to us, making them detectable even across vast distances. Another area of research involves looking for unusual patterns in starlight. If a planet has large artificial structures or orbiting technologies, it might cause irregular dimming of its star. While natural explanations are always considered first, these kinds of anomalies are of great interest to scientists studying potential technosignatures. The search for extraterrestrial intelligence is not limited to radio telescopes on Earth. Space-based observatories are also being used to scan for unusual signals and patterns. These instruments can avoid interference from Earth's atmosphere and expand the range of frequencies that can be observed. As technology improves, our ability to detect faint or distant signals continues to increase. One of the major challenges in SETI research is distinguishing between natural and artificial signals. The universe is full of complex and dynamic processes that can produce unusual patterns. Pulsars, quasars, and other astronomical objects can sometimes mimic artificial signals. Careful analysis is required to determine whether a signal is truly non-natural in origin. Another challenge is the sheer scale of the search. The galaxy contains hundreds of billions of stars, and only a small fraction of them can be observed in detail at any given time. Even if intelligent civilizations are common, their signals may be weak, rare, or directed in ways that make them difficult to detect from Earth. This means that the search space is enormous, and we have only explored a tiny portion of it so far. Time is also an important factor. Civilizations may not exist at the same time. A civilization could send signals for a brief period and then cease to exist or stop transmitting. Given the vast timescales involved in cosmic evolution, the likelihood of two civilizations overlapping in both time and space may be extremely small. This temporal mismatch could help explain why we have not yet detected any signals. Despite these challenges, the search continues because the potential discovery would be so significant. Detecting even a single confirmed technosignature would fundamentally change our understanding of the universe. It would show that intelligent life is not unique to Earth, and that other civilizations have developed technology capable of interacting with the cosmos. SETI also raises important philosophical questions. If we were to detect a signal, how should we respond? Should we attempt to reply or simply observe? What would communication with another civilization look like, especially if they are far more advanced or fundamentally different from us? These questions are not just scientific, but also deeply human. Some researchers have also considered the possibility that we might already be receiving signals but are not recognizing them. An advanced civilization might use communication methods that are currently beyond our understanding. Just as early humans would not have understood radio waves, we may not yet be equipped to interpret certain types of extraterrestrial communication. Another idea is that civilizations might communicate in ways that are not intended for direct contact. Signals could be indirect, such as environmental modifications or large-scale changes to planetary systems. These would not be messages in the traditional sense, but they could still indicate the presence of intelligence. In recent years, the search for technosignatures has expanded beyond radio astronomy into the study of exoplanet atmospheres. If a civilization alters the composition of its planet's atmosphere, either through industry or large-scale engineering, it might create detectable chemical signatures. These could include unusual levels of gases that are not easily explained by natural processes. For example, certain industrial gases do not occur naturally in large quantities on Earth. If similar compounds were detected in the atmosphere of another planet, it could suggest technological activity. However, as with all SETI research, alternative natural explanations must always be carefully considered. The search for extraterrestrial intelligence is ultimately a search for patterns. It is about identifying signals that stand out from the natural background of the universe. It requires both technological capability and careful interpretation. It also requires patience, because the signals we are looking for may be rare, distant, or subtle. Even if no signals are found, the search itself is valuable. It helps us understand the limits of our technology, the nature of the universe, and the conditions under which life and intelligence might arise. It also forces us to consider what it means to be a technological civilization in a vast and possibly silent cosmos. As we continue to explore the universe, SETI remains one of the most profound scientific efforts of our time. It represents the idea that we are not only observers of the universe, but also potential participants in a larger cosmic network of intelligence. Whether that network exists or not remains unknown. But the search continues, driven by curiosity, by possibility, and by the fundamental question that lies at the heart of it all. Are we alone, or is the universe already speaking in ways we have not yet learned to hear? As the search for extraterrestrial intelligence continues, one of the most puzzling questions in all of science becomes impossible to ignore. If the universe is so vast, filled with billions of galaxies, each containing billions of stars and even more planets, then where is everybody? This question, simple on the surface, leads to one of the deepest paradoxes in modern astronomy. It is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously questioned why we have not observed any evidence of extraterrestrial civilizations despite the high probability that they should exist. At its core, the Fermi Paradox is a contradiction between expectation and observation. On one hand, the universe appears to be extremely old and vast. On the other hand, we see no clear signs of advanced civilizations beyond Earth. If intelligent life is common, then some civilizations should have had enough time to develop advanced technology, explore the galaxy, and possibly leave detectable traces of their existence. Yet when we look at the night sky, we see silence. This silence becomes even more striking when we consider the age of the universe. The Milky Way galaxy is over 10 billion years old. Earth, by comparison, is only about 4.5 billion years old. This means that many stars and planetary systems formed billions of years before our own solar system even existed. If life can arise on planets under the right conditions, then it is possible that other civilizations could have emerged long before humanity appeared. Given enough time, even slow interstellar travel becomes significant. A civilization capable of sending probes or self-replicating machines across space could, in theory, spread throughout the galaxy over millions of years. Even at speeds far below the speed of light, such expansion could eventually reach every star system in the Milky Way. This idea leads to an expectation that if intelligent life is common and long-lived, the galaxy might already be filled with signs of its presence. Yet we see no such evidence. This is the heart of the paradox. The more we learn about the size and age of the universe, the more surprising the silence becomes. There are many possible explanations for this contradiction, and each one carries profound implications. One possibility is that intelligent life is extremely rare. While simple life might be common, the transition from simple organisms to complex intelligence capable of technology might be an extremely unlikely event. If this is true, then Earth may be one of the few places where this transition has occurred. Another explanation is that intelligent civilizations tend to destroy themselves before they become widespread. This idea is often referred to as the Great Filter hypothesis. The Great Filter could be any stage in the development of life, from the origin of life itself to the emergence of intelligence or even the survival of technological civilizations. If the filter lies ahead of us, it suggests that many civilizations fail to survive long enough to become detectable on a galactic scale. Self-destruction could take many forms. Nuclear war, environmental collapse, uncontrolled artificial intelligence, or other unknown risks could limit the lifespan of technological civilizations. If civilizations typically last only a short time on cosmic scales, then the chances of overlapping with another civilization in both time and space become extremely small. Another possibility is that advanced civilizations do exist but choose not to expand or communicate in ways we can detect. This idea suggests that technological societies may eventually reach a point where expansion is no longer desirable or necessary. They might focus inward rather than outward, developing in ways that do not produce large-scale energy emissions or interstellar signals. In this scenario, civilizations might become quiet by choice or by evolution. They may transition into forms of existence that are highly efficient, low energy, or digital in nature. If they no longer emit detectable signals, they would effectively become invisible to our current methods of observation. A related idea is that civilizations may intentionally avoid contact with others. This is sometimes referred to as the dark forest hypothesis, where intelligent civilizations remain silent to avoid potential threats. In a universe where intentions are unknown and distances are vast, silence could be a form of protection. While this idea is speculative, it reflects the uncertainty that comes with imagining other intelligent beings in the cosmos. Another explanation focuses on the limitations of our own technology. It is possible that civilizations are sending signals, but we are not capable of detecting or recognizing them. Our instruments may only be sensitive to a narrow range of frequencies or signal types. Advanced civilizations might use communication methods that are completely different from radio waves or other technologies we currently understand. There is also the possibility that interstellar travel is far more difficult than we assume. The energy required to travel between stars is enormous, and the physical challenges are significant. Even if civilizations are capable of space travel, they may find it more efficient to remain within their own planetary systems. If interstellar expansion is rare or impractical, then the galaxy may remain largely isolated, despite the existence of intelligent life. Some scientists also consider the idea that we are early in the history of the universe. While the universe is very old, conditions suitable for life may have become more common only in relatively recent cosmic history. If this is the case, then intelligent civilizations may not have had enough time to develop and spread widely. We may simply be among the first. There is also the possibility that life is common, but intelligence is not. Evolution on Earth shows that complex intelligence is not an inevitable outcome. For most of Earth's history, life existed in simple forms. Intelligence capable of technology appeared only very recently. This suggests that the emergence of intelligence may depend on a series of rare and contingent events. Another idea is that civilizations may exist in forms that are fundamentally different from what we expect. We tend to imagine extraterrestrial intelligence in terms similar to our own, with technology, communication, and expansion. But it is possible that alien intelligence operates in ways that are not compatible with our methods of detection. They may exist in digital environments, artificial substrates, or forms of collective intelligence that do not interact with physical space in obvious ways. Some explanations also consider the role of time delays in communication and observation. Even if civilizations exist, the vast distances between stars mean that signals take thousands or even millions of years to travel. By the time a signal reaches us, the civilization that sent it may no longer exist or may have evolved beyond recognition. This creates a fragmented and incomplete picture of the galaxy. The Fermi Paradox also forces us to consider the possibility that we are looking in the wrong way or at the wrong scales. Our search methods are based on assumptions derived from our own technological development. If those assumptions are incorrect, we may be missing signals that are present but not recognizable. Despite the many proposed explanations, there is no consensus. The Fermi Paradox remains unresolved because it sits at the intersection of astronomy, biology, physics, and philosophy. It is not a single problem with a single solution, but a collection of uncertainties that together create a profound mystery. What makes the paradox so powerful is not just the absence of evidence, but the expectation that evidence should exist. Given the age and size of the universe, the emergence of intelligent life somewhere else seems statistically plausible. Yet the silence persists. This tension between expectation and observation is what makes the question so compelling. It is important to recognize that the Fermi Paradox does not prove that we are alone. It only highlights the gap between what we might expect and what we currently observe. As our technology improves and our search expands, this gap may begin to close. New instruments, new methods, and new ideas may eventually reveal signals or patterns that we have not yet detected. Until then, the paradox remains an open question. It challenges our assumptions about life, intelligence, and the nature of the universe itself. It forces us to confront the possibility that either life is rare, civilizations are short-lived, or our understanding of the cosmos is still incomplete. In the end, the Fermi Paradox is not just about silence. It is about perspective. It reminds us that we are searching from a single point in a vast universe, trying to understand a system far larger and more complex than anything we have ever experienced. Whether the silence means we are alone or simply early in the story of cosmic evolution is a question that remains unanswered. And so we continue to listen, to search, and to wonder, knowing that somewhere in the vast darkness of space, the answer may already exist, waiting for us to find it, or perhaps waiting for us to become capable of understanding it. As we reach the final stage of this exploration into the search for extraterrestrial life, we are left with more questions than answers, but also with a far deeper understanding of the universe than at any point in human history. The journey has taken us from ancient speculation to modern science, from philosophical curiosity to data-driven investigation. We have examined planets, moons, stars, and galaxies, and we have explored the conditions that might allow life to emerge beyond Earth. Yet the most important realization is not what we have found, but how much remains to be discovered. The future of this search depends on technology that is still being developed today. New generations of telescopes are being designed to look deeper into space and with greater precision than ever before. These instruments will allow scientists to analyze the atmospheres of distant exoplanets in unprecedented detail. By studying the light that passes through these atmospheres, we may be able to detect chemical signatures that suggest biological activity. One of the key goals of future space telescopes is the detection of biosignatures. These are patterns in a planet's atmosphere or surface chemistry that could indicate the presence of life. For example, the simultaneous presence of oxygen and methane in a stable atmosphere could be difficult to explain without biological processes. On Earth, these gases are maintained by living organisms. If similar patterns are found elsewhere, they could provide one of the strongest hints yet that life exists beyond our planet. However, interpreting biosignatures is not straightforward. Many non-biological processes can produce similar chemical signatures. Geological activity, photochemical reactions, and atmospheric interactions can all mimic the signals of life. This means that future discoveries will require careful analysis and multiple lines of evidence before any conclusion can be drawn. Another major development in the search for life is the study of exoplanet climates and environments in much greater detail. Instead of simply identifying planets within habitable zones, scientists are now beginning to model entire planetary systems. These models take into account atmospheric composition, surface conditions, orbital dynamics, and stellar behavior. By combining all of these factors, researchers can estimate how likely a planet is to support stable environments over long periods of time. At the same time, advances in technology are allowing us to study smaller and more distant planets than ever before. Space-based observatories are being developed with the ability to directly image exoplanets, separating their light from the overwhelming brightness of their host stars. This will allow scientists to observe planetary surfaces, cloud systems, and atmospheric changes in real time. One of the most ambitious goals of future exploration is the direct detection of Earth-like planets in nearby star systems. These planets would be close enough for detailed study, potentially allowing us to analyze their atmospheres for signs of life. If such a planet is found, it would represent one of the most important discoveries in human history. Beyond telescopes, space missions within our own solar system continue to play a critical role in the search for life. Missions to icy moons such as Europa and Enceladus aim to explore subsurface oceans that may contain the ingredients for life. Future spacecraft may attempt to land on these moons, drill through their ice layers, or collect samples from their plumes. These missions could provide the first direct evidence of life beyond Earth, if it exists within our own cosmic neighborhood. Mars also remains an important target. Although its surface is cold and dry today, there is strong evidence that Mars once had liquid water and a more Earth-like environment. Ancient riverbeds, lake beds, and mineral deposits suggest that conditions on early Mars may have been suitable for life. Future missions aim to search for signs of ancient microbial life preserved in rocks and soil. If even microbial life is discovered on another world, it would have profound implications. It would suggest that life is not unique to Earth and that the universe may be filled with living systems. It would also raise new questions about how life originates and whether it arises independently in different environments or spreads between worlds through processes like meteor impacts. One of the most exciting areas of future research is the study of technosignatures. While biosignatures indicate biological activity, technosignatures indicate technological activity. These could include radio signals, laser emissions, large-scale energy usage, or even artificial structures that alter the appearance of a star or planet. Future radio telescopes will be far more sensitive than current instruments. They will be able to scan larger regions of the sky and detect much weaker signals. This increases the chance of identifying artificial transmissions, if they exist. At the same time, optical telescopes may be able to detect laser-based communication or other advanced technologies used by distant civilizations. Another possibility is the detection of large-scale engineering projects. If a civilization becomes highly advanced, it may construct massive structures that influence the light of its star. These structures could create unusual patterns in starlight that might be detectable from Earth. While no such evidence has been found, future instruments may be capable of identifying subtle anomalies that were previously invisible. Artificial intelligence will also play a major role in the future of this search. The amount of data generated by modern telescopes is enormous, far beyond what humans can analyze manually. Machine learning systems are already being used to identify patterns, filter noise, and detect unusual signals. As these systems become more advanced, they may be able to recognize subtle signs of life or technology that humans would miss. Another important development is the possibility of interstellar exploration. While current spacecraft are limited to our solar system, future propulsion technologies could allow us to send probes to nearby star systems. These probes could directly study exoplanets, gather data, and potentially even search for signs of life up close. Although such missions would take decades or centuries, they represent a long-term path toward direct exploration of other worlds. As we look to the future, it is also important to consider the philosophical implications of discovery. If we find life elsewhere, it will fundamentally change our understanding of our place in the universe. It would show that life is not unique to Earth, and that we are part of a broader cosmic community of living systems. If we find intelligent life, the implications become even more profound, raising questions about communication, ethics, and shared existence across interstellar distances. If we do not find life, that result is also significant. It may suggest that life is extremely rare, or that intelligent civilizations are short-lived or isolated. It could also mean that our methods of detection are still insufficient. In either case, the absence of evidence would still shape our understanding of the universe. The future of this search is not limited to science alone. It also involves philosophy, imagination, and human curiosity. The question of whether we are alone in the universe is deeply connected to how we understand ourselves. It touches on ideas of origin, purpose, and connection. It asks whether life is a common feature of the cosmos or a rare and fragile phenomenon. As technology continues to advance, our ability to explore these questions will grow. We are moving into an era where we can study planets around other stars in detail, analyze their atmospheres, and search for subtle signs of life. We are also developing the tools needed to explore our own solar system in greater depth than ever before. Each discovery, whether it confirms or challenges our expectations, will bring us closer to understanding the true nature of life in the universe. The search itself is a process of expansion, not only outward into space, but also inward into our understanding of biology, chemistry, and existence. In the end, the future of this journey is not defined by a single discovery, but by a continuous process of exploration. We are building the tools, refining the theories, and expanding the boundaries of what we can observe. Somewhere in the vastness of space, there may be answers waiting for us, or there may be new questions we have not yet imagined. What remains certain is that the search will continue. It will continue because it is driven by one of the most fundamental aspects of human nature, the desire to understand whether we are alone. And as long as that question remains unanswered, we will keep looking deeper into the universe, listening more carefully, and reaching further than ever before.